Hi, everyone. Thank you for joining us today. We're just going to give it a moment for everyone to jump in the webinar, and then we'll get started today. Okay, great. Looks like we have a good amount of people in our webinar now, so let's get started. Hi, everyone. My name is Courtney Brown, and I'm a Senior Marketing Manager here at EDB. I'm going to be your host today for our webinar, Cloud Native PostgreSQL. Before I turn it over, I'm going to go through a few housekeeping items. This presentation is being recorded. We're going to share the recording along with the slides after the broadcast to the email address that you used to register for the webinar. All of your lines are currently muted, but if you have a question, please feel free to submit it into the question panel. We expect the presentation is going to last most of our time today, but any extra time we're going to allot to live Q&A. If we don't have time to address all of your questions, we'll be sure to follow up afterwards with anyone who didn't have their question answered. Now, before we start, I'm going to launch a quick poll for all of you. We want to know where you currently are in your cloud native journey with Kubernetes. So go ahead, take a moment, look at the different options, select the one that is most relevant to you, and then we'll share with everyone before we get started. Looks like a lot of people are just starting to explore. We'll give a moment to make sure a majority of the audience has a chance to vote. Okay, it looks like we have a good amount. So I'm going to end our polling and share the results with everyone. Should now be able to see. Okay, great. And with that, I'm going to pass it over and we can start our session.
Okay, so where are you now in your cloud native journey with Kubernetes? And where do you plan to be in the future? But most importantly, how do you feel about using Kubernetes to continuously deploy your stateless applications that talk to a PostgreSQL database? So welcome to this webinar about cloud native PostgreSQL brought to you by Enterprise DB. My name is Gabriele Bartolini, and I'm leading the Cloud Native initiative here at EDB. Today, I will provide you with an overview of version 1.10 of Cloud Native PostgreSQL, our operator for Postgres workloads in Kubernetes. So before I start, I'd like to take a few seconds to introduce myself. I've been using Postgres for almost 2 decades now, and I've been a member of the community for the last 15. Second quadrant has certainly represented the most significant part of my professional experience with Postgres. And I joined the founder, Simon Riggs, in 2008 and covered several roles, including CEO of Second Quadrant Italy, head of global support, and lead of the Cloud Native initiative. I'm also one of the founding members and contributors of Barman, the backup and recovery manager tool for Postgres. My experience and enthusiasm are now part of EDB, which recently acquired Second Quadrant. So Cloud Native is not just about tools. It's also about a culture that derives from DevOps, DevSecOps, Lean and Agile methodologies, and the outcomes in terms of processes, patterns, and tools. Cloud Native is about architectures that are based on microservices and that rely on Linux containers. And of course, when it comes to managing several containers and how they run on different hosts, Kubernetes is the de facto standard. So this is the agenda for today. After an introduction on Cloud Native Postgres, we'll go through some architectural aspects, the operator capabilities, and configuration of Cloud Native Postgres. We'll then conclude with some information about storage. So just for those of you who are not familiar with EDB, EDB is now the largest dedicated company that operates on the PostgreSQL database in the world. This is especially true now after the acquisition of Second Quadrant, which was my previous company, in September 2020. EDB is a member of both the Linux Foundation and the Cloud Native Computing Foundation. And most importantly, we are a Kubernetes certified service provider, KCSP. And we are the first company in the PostgreSQL ecosystem to reach this status. We build our container images based on Red Hat UVI images and publish them on key.io. Our software is also certified on Red Hat OpenShift. And our efforts are concentrated on two major products: an operator for Postgres called Cloud Native Postgres, and an operator for BDR called Cloud Native BDR, which will be, the first version will be out by the end of this quarter, okay? So we have just launched Cloud Native Postgres a month ago, which is a product entirely and exclusively designed for Kubernetes. It's a Kubernetes operator written directly in the Go language that is fully integrated with the Kubernetes API server. It relies solely on Kubernetes to manage high availability, and as such, we don't rely on external tools which are also intended for traditional contexts, such as Rep Manager, which, by the way, we built at Second Quadrant, or Patroni, or Stolon, or other tools like EDB Failover Manager, for example. We build immutable application containers for PostgreSQL 10 or higher, and for EDB Postgres Advanced 10 or higher. If you want to know more about immutable application containers, there's a blog article that I recently wrote about this. And in general, please feel free to follow us on our, in our Kubernetes section in the blog for EDB. We are planning to release BDR 3.6, as I mentioned before, later in this quarter. So Cloud Native Postgres is a Kubernetes operator, but what's that exactly? So an operator is an extension of the Kubernetes controller, which defines how a complex application works in business continuity contexts. It kind of simulates the work of a human operator in an automated and programmatic way. So specifically, we are interested in Postgres. Postgres is a complex application, and an operator not only needs to deploy a cluster, which is the first step, but also to properly react after unexpected events during the normal life cycle of the database. The typical example of such an unexpected event is the failover. So an operator relies on Kubernetes for capabilities like self-healing, scalability, high availability, updates, access, resource control, and so on. It's designed to be fully automated and to support declarative configuration. So the easiest way for me to explain declarative configuration, given that the majority of you is, started to explore Kubernetes, okay? So it's important, I think, to spend, some time on this concept. So the easiest way for me to explain declarative configuration is through an example that highlights the differences with the opposite, imperative configuration. So in an imperative context, the state is defined as a series of tasks that needs to be executed in sequence. So I can get a 3-node Postgres cluster by creating the first instance, then configure the replication, clone a second instance, and repeat the same process for the third one. So the second level. In a declarative approach, the state of the system is instead defined through configuration. So in this case, we can simply say there's a PostgreSQL 13 cluster with 2 replicas. This approach highly simplifies change management operation. And when these are stored in source control systems like Git, it enables the infrastructure as code capability. The good thing is that with Kubernetes, this goes even farther than deployment, as Kubernetes makes sure that our request is fulfilled not only at deploy time, but at any time. So why did I mention the concept of state? Because I mean, the reason is that that's, according to me, but yeah, many people that work in Kubernetes as well, that's the best way to explain why Kubernetes is so important, the concept of state. Kubernetes allows us to define as configuration the desired state of an object, of a group of objects, and therefore consequently the overall infrastructure as a group of objects. Kubernetes continuously makes sure that the current state of the infrastructure matches the desired one through the so-called reconciliation loops, which are initiated by the Kubernetes controller. If the desired state and the actual state don't match, reconciliation loops trigger self-healing procedures. That's where operators come into play. So to clarify this concept, I want to describe what we expected, okay, from a Postgres operator when we conceived it, and through an example. Okay, so we request Kubernetes to deploy a new PostgreSQL 13 cluster with 2 replicas by defining a desired state, which is what you find on the left side of this image. Then the controller, through reconciliation loops, detects that the current state, 0 instances, differs from the desired state, 1 primary and 2 replicas, and invokes the cloud-native Postgres operator, in our case, to create the primary. Then clone the first replica and the second replica. In case of failure of a standby, for example, the reconciliation loop detects that event and initiates a self-healing procedure that either restarts the instance by using the same persistent volume, or recloning it entirely for more severe cases where we lost, for example, the persistent volume. Similarly, in case of failure of the primary, the operator promotes the most aligned replica and restarts the former primary as a standby by making it follow the new primary. The operator also supports scaling up and scaling down. So that is what we wanted. And that is how we implemented Cloud Native Postgres, an operator for Kubernetes that allows us to deploy PostgreSQL clusters with the primary and standby architecture. So our operator has been designed to support custom application images, which enable to seamlessly work with either PostgreSQL and EDB Postgres Advanced, as I mentioned before, both from version 10. Our containers are currently hosted on key.io and are generally available under the Enterprise DB limited use license. The documentation is available at the docs.enterprisedb.io and is publicly accessible. So in the traditional VM-based and mutable mindset, so mutable infrastructure mindset, we are used to think in terms of packages. So although we internally use packages to build our containers, the way software, and in particular immutable software, is distributed in Kubernetes is via container images. So container images are the new packages, okay? Our container images are built on Red Hat UBI 8, except EDB Postgres Advanced 10 and 11, which are built on UBI 7. This means that we use our our PGDG or EDB RPMs to install Postgres. depending on the case. There are two types of container image we distribute: the operator image, which is a Go application, and the operand image, which represents the application that the operator controls, in our case, Postgres. At the moment, we build two families of application containers: the PostgreSQL ones, distributed under the Postgres license, and the GNU GPL3 license for Barman Cloud, and the EDB Postgres Advanced images that are distributed under the EDB Limited Use license. The Postgres container images are open source and provide also an entry point which enables rapid testing of Postgres in Docker. You can find them in our GitHub repositories. So our goal is to run Postgres wherever Kubernetes runs. So by supporting all Kubernetes versions and Red Hat OpenShift 4, we are able to target both private cloud and self-managed scenarios in general. So by supporting Azure, AWS, and Google Cloud, by the way, AWS and Google Cloud are expected for the second quarter of this year, we are able to cover the majority of public cloud scenarios. As a result, we want to introduce support for multi-cluster setups, opening up for both hybrid, meaning a mix of public and private clouds, and multi-cloud scenarios with multiple cloud providers in public cloud providers involved. So multi-cloud and hybrid cloud. As anticipated earlier, Cloud Native Postgres has been designed for Kubernetes. We build on immutable application containers, which run only Postgres and are very light. We rely on declarative configuration, which is essential for the infrastructure as code paradigm, and deployments and interaction with Postgres cluster go through kubectl and YAML files to control the desired state. So our command line interface is kubectl. Okay, so if you are, like us, as certified Kubernetes administrator, you understand what that means. In terms of architectures, it is probably too early now to understand all the possible use cases. Okay, however, we can anticipate these two main architectures based on where the application resides, inside Kubernetes or outside. The first use case is the best experience of Cloud Native Postgres. As thanks to infrastructure abstraction, it creates an end-to-end highway between the developer and the end user of the application. It removes variability between development, staging, and production environments, and enables CI/CD pipelines at application level, including continuous deployment for high-performing organization. That's the true DevOps experience. Technically, the stateless application is managed as a deployment with an underlying replica set, and it is exposed externally through an ingress. The database is managed by the operator, which exposes a service to the application. Whereas in the second case, the applications reside outside the Kubernetes cluster. These are either legacy applications or applications that are in the process of being containerized. The application is hosted on traditional environments, and the database is exposed externally via TCP and TLS through an ingress. This is a diagram that provides more details on the components for the application and database in Kubernetes scenario. So I will briefly state that the stateful component relies on Postgres pods that are managed directly by our cluster custom resource definition. So applications talk to the database via the service that is managed by the cluster CID. So Cloud Native Postgres implements the primary standby architecture with an arbitrary and optional number of hot standby streaming replicas both asynchronous, which is default, or synchronous. Standby servers are required for high availability, of course. And self-healing required us to introduce support, native support, and transparent support for PG rewind in case the timeline diverges. The cluster can be accessed by the applications via two Kubernetes services, via three Kubernetes services. The RW service, so there's a suffix, RW, R, and RO. R is read workloads, and RO is read-only workloads that's being released today. RW is read-write workloads. So this is the picture that depicts how applications interact transparently with the cluster through the service, the RW service for read-write operations. And this is for the read service. So what are the capabilities of the operator? We decided to adopt the operator capability levels framework, which is part of the operator SDK project. So we are currently sitting on stage 3 out of 5, which is full life cycle, and we're aiming to reach completely level 4 in the next quarter. So capability level 1 involves installation and configuration of the operator. In this category, we include usability and user experience enhancements, as well as InfoSec matters. Capability 2 is about enabling updates of the operator and the actual workload. So in our case, Postgres servers. This includes Postgres minor releases, like security and bug fixes, as well as major online upgrades. Capability level 3 requires the operator to manage aspects of business continuity and scalability. Capability level 4 is all about observability, so monitoring, alerting, trending, log processing, and that might involve use of external tools such as Prometheus, Grafana, Fluentbit, as well as extensions in Postgres, for example. Level 5 is focused on automated scaling, healing, and tuning through the discovery of anomalies and insights that emerged from the observability layer. So we have already implemented some critical features in this level. So once we fix level 4, we will already be at level 5. So in terms of clusters management, Cloud Native Postgres implements self-healing capabilities such as failover and replica creation via liveness and readiness probes as required by Kubernetes. The life cycle is completed with switchover, rolling updates, and scaling capabilities. In terms of storage management, we support persistent volume claims, as well as storage classes for dynamic provisioning of storage. As a result, our users have complete freedom of choice and use on any of the supported storage technologies in Kubernetes, both on a network or local. I will provide more details about this. There's a section later on in this webinar. Shortly, I'll be covering that. So the only way to upgrade an application container is to replace it with an updated version of the image. This means that a minor update of Postgres, of a Postgres version, means that the container image of PostgreSQL 13.1, for example, is replaced with the 13.2.1 without touching the persistent volume. So Cloud Native Postgres is designed to handle this kind of operation similar to Kubernetes deployments. It does it in a rolling upgrade fashion by first replacing one by one all the Postgres replicas, and then the old primary after switching over to a promoted and updated replica. Such switchover operation can be fully automated or manual, there's a setting called update strategy that can be supervised or unsupervised. By default, it's unsupervised. Rolling updates are also triggered when a change in PostgreSQL configuration requires a restart. And rolling updates in general are one of the main reasons why we decided not to use replica sets or stateful sets when writing our operator. So this is a very important capability. And there's again, this blog article here covers some of these aspects as well. So there's a series of articles on security that we're writing. So I really encourage you to read and provide feedback. So as far as security is concerned, we adapted our product to the 4C security model of Kubernetes, which is performed at four layers. So 4C stands for cloud, cluster, container, and code layers. So please, follow us on Twitter and LinkedIn to receive updates about our blog articles. So we support security contexts and pod security policies. And it is important to understand that thanks to immutable application containers, we don't need root privileges to run our containers or to access storage volumes. We support TLS encryption and secrets. And as far as source code is regarded, we systematically perform static code analysis in our pipelines. If you are familiar with TLS certificates with Postgres, you know how, but in general as well, how tedious and error-prone the process is. The good thing about Cloud Native Postgres is that it automates all of that for us by transparently creating a certification authority for the operator and one for each PostgreSQL cluster that we create. This enables us to turn on encrypted connections using TLS and support client authentication based on TLS certificates in general. So by default, the streaming replication standby servers, for example, connect to the primary using a TLS certificate that Cloud Native Postgres automatically creates. Today, with release 1.10 of Cloud Native Postgres, we introduced the kubectl plugin with a command called certificate that allows us to generate TLS certificates for the applications. So in terms of continuous physical backup, we have used all our 10+ years experience with Barman in designing backup and recovery support. We currently support continuous backup on object stores that are S3 compatible, so both in public and private cloud, for example, using Min.io. We rely on Barman CloudWall Archive for wall shipping via archive command, which is transparently done by the operator, and Barman Cloud Backup for scheduled or on-demand backups. As you've noticed, we don't yet support the full Barman, just the cloud utilities. Recovery for us is a way to bootstrap a new cluster by restoring from a previous backup either fully, which means until the end of the archive, or up to a point in time. We do support all options available in Postgres for point-in-time recovery. Even in this case, we currently rely on Barman Cloud, specifically Barman Cloud Restore to uncompress the base backup, and Barman Cloud Wall Restore to pull wall files on demand from the bucket. So it is now time to introduce the cluster resource, which is how we enable users to define a Postgres cluster in a declarative way. It is conceptually similar to a deployment type in Kubernetes, but it embeds the primary standby logic of Postgres and directly knows the internals of Postgres to promptly and correctly inform the Kubernetes API about the state of the entire Postgres cluster. The instances parameter defines the total number of instances, with instances -1 being the number of standby servers or replicas. We adopted the convention over configuration paradigm, which, by the way, we had already successfully implemented the environment. This YAML file is sufficient to create a PostgreSQL 13.2 cluster called MyAppDB, made up of 3 instances, which means 1 primary and 2 standby servers, each with requested storage allocation of 10 gigabytes using the default storage class. That's very neat. kubectl apply is the way in Kubernetes to apply changes to the cluster state. The first command is all it takes for you to install our operator or update it. The second one is the command that you need to run to install a new cluster using the provided YAML file as definition, for example, this one, okay? So we don't need 10 steps or 20 pages in the manual to install Postgres, just 2 commands, okay? One for the operator and one for the class. Postgres configuration must be managed by the parameters dictionary of the PostgreSQL map in the cluster specification. The operator has been designed to automatically manage reload and, if required, restart the Postgres instances following a change of the configuration parameters. There's a limitation. Currently, the operator is not able to correctly manage standby sensitive settings that must always have an equal or greater value than the primaries, such as max connections or max world senders, but we're working on that, so that will be done in the next releases. By default, all replicas are configured through convention of a configuration in an asynchronous stream replication mode. However, you can configure stream replication, synchronous stream replication very easily using these 2 parameters: min sync replicas, which is the minimum number of instances required to be in synchronous replication, and max sync replicas, which is the target value for synchronous replication quorum. I was mentioning the command line interface for us is kubectl, the same for Kubernetes. We have developed a plugin called CNP for kubectl that you can use to perform operations such as switchover, TLS certificate generation, or display the status of the cluster, like in this case. So let's get now to talk a bit about storage. Okay, so we all know that storage is critical in a database context. We all expect that storage is available, can scale, performs well, and guarantees both consistency and durability. So we as Postgres people, Postgres administrators, normally associate availability of the storage with that of the hosting operating system. And scalability is achieved either via table spaces, LVM, or storage online resizing capabilities of the storage. As a result, when it comes to Postgres, we tend to focus primarily on performance, consistency, and durability. Fortunately, when it comes to storage access patterns, the same concepts as in VM and bare metal environment are still valid in Kubernetes when we talk about Postgres. We just need to integrate all this valuable knowledge with how Kubernetes manages storage, that is, storage classes, persistent volumes, and persistent volume claims. There are primarily 2 methods of access to storage. The first one is via network, either directly or indirectly. Think, for example, of an NFS volume that is attached to the VM hypervisor and used as a local volume in the machine, the virtual machine. Network storage is the most used pattern in Kubernetes, and there's a labyrinth of available solutions, either outside the Kubernetes cluster or inside the Kubernetes cluster. Normally, replication is at file system level. Network storage in Kubernetes presents the same issues of throughput and latency that we have all experienced with Postgres in traditional environments. The second method on the right is local storage. That means local to the Kubernetes node where a pod is running. This also includes directly attached disks, which database people like us love. But this is an anti-pattern in Kubernetes. So, however, I must admit that the Kubernetes community is changing and there's work happening in the shared nothing architecture direction with local persistent volumes and open source products like, for example, OpenEBS or Topwall VM, or even, the default local storage in Kubernetes. We know the benefits of shared nothing architecture, but we also know the main limitation, which is easier scalability. Although there are several possible combinations and examples, due to time constraints for this webinar, I have selected two simplified architectures, one for network and one for local storage. The first example is an architecture of Postgres hosted on network storage that uses native streaming replication for high availability. This is Kubernetes Postgres will work here, but for performance reasons, because of lack of predictability in performance, we prefer the other approach. Okay, but you understand all the issues that we can have with network storage. This is an example instead of local storage with Postgres replication, which is what we recommend for cloud-native Postgres. And thanks to the levels of abstraction and extensibility that Kubernetes provides, the same pattern is applicable in all contexts, both in private and public clouds. So preferably, we'd like to rely on disk that not only is locally mounted, but that is dedicated or even directly attached to the node where a Postgres pod is running. I know that Kubernetes people might think I'm crazy, but that's where we're trying to go, okay? Not excluding the other solution, okay? So this means that we can implement the shared nothing architecture for Postgres even in Kubernetes, which is fundamental in very large database contexts. In fact, if needed, a Kubernetes worker node can be dedicated to a single Postgres cluster, using its own dedicated hardware RAID controller with local solid-state drives, or even its own SAN. So if you have time, this is an article I recommend. So when we were at second quadrant, we pioneered the local storage use case for databases in Kubernetes. And in May 2020, we published this article, which became quite popular in the Kubernetes database community. And we are planning to update it and rebrand it in the next weeks or months. So the benchmark compared file system performance on bare metal, the way we used to do, for example, at second quarter using Bonnie++, with file systems in Kubernetes. And we chose two configurations: local storage using the open source local persistent volume provided by OpenEBS, and network storage using CStore. So without going into much details, this is the Kubernetes cluster we adopted, and the results went beyond our expectations. So in terms of sequential reads, the bare metal test reached a throughput of 1 GB per second. The test inside Kubernetes, 964 megabytes per second, only 3% lower than bare metal. It went even better in terms of sequential writes, where performance was almost identical. As you can see, the performance of network storage, which is quite common in Kubernetes nowadays, is not even comparable to the local one. However, we will need to cope with this. Okay? So we also ran OLTP-like tests on Postgres using pgbench. So with just two physical solid-state drives, we were able to reach 3.8 thousand transactions per second against the 4.2 thousand on bare metal. Again, you can appreciate the difference between local setup that we are pioneering in Kubernetes and what we will probably encounter encounter very often in the future in Kubernetes. So the message here is that we've opened a new frontier. We not only can operate on standard and typical network storage setups in Kubernetes, but we open up the possibility to use dedicated storage too, which is fundamental for very large databases and critical context. We've demonstrated that performance in Kubernetes is almost comparable to bare metal, with all the benefits of Kubernetes in terms of business continuity. That's where we at EDB want to be. So the road ahead of us for cloud-native Postgres is long, but we have a solid plan and commitment. So we plan to improve logging and monitoring with a native Prometheus exporter that allows us to configure custom queries via config map or cluster level. This will be ready, I'd probably say in the next version or two. We want to improve pooling facilities to address users with more strict performance requirements as well as replication. For example, we want to be able to bootstrap a new cluster using another Postgres cluster inside or outside Kubernetes, having the same major release, and request for that cluster to operate in continuous recovery as a replica cluster. This allows us zero cutover time migrations to Kubernetes for Postgres 10 or higher, as well as the setup of replica clusters in different regions using cascading replication and independent backups. We also want to add support to logical replication, with an important use case being major online upgrades of Postgres. As creators of Barman, we want to write a Barman operator that enables management of Barman in Kubernetes with transparent integration with clusters created with our operator. We also want to explore persistent volume snapshots for those storage classes that will support it. Finally, we need to explore the area of Kubernetes federation, where Kubernetes is working over multiple regions and coordinating different clusters. This is a hot topic in Kubernetes, and we will need to monitor how Kubernetes will solve this natively and then adapt. We're also looking to, for example, solutions like Rancher, which seems a very good solution in this area. But in general, we will work on improvements also that come from customers and users base. So how can I test cloud-native Postgres? Cloud-native Postgres can be freely and independently evaluated by everyone now. So we decided to differentiate between Postgres and EDB Postgres Advanced in terms of evaluation. So with Postgres, you can start a cluster without requesting a license key. So an implicit 30-day trial license is created for the cluster. And after that day, all reconciliation loops are stopped. With EDB Postgres Advanced, a license key is required to start. It's necessary to request a trial from the website, which lasts 60 days from the day of issue. So we will introduce further options in the future, like corporate trial licenses, for example, but that's something that we are exploring. So with cloud-native Postgres, you can get the best of the two worlds. So use the extensive set of features that the community Postgres provides on the most advanced open source container orchestrator that is Kubernetes. As a last remark, the key aspect to understand is that Kubernetes, sorry, I had hijacked by the daughter. The key aspect to understand is that with Kubernetes, all applications coexist in the same distributed system. So when referring to applications, we include also databases. So if you've worked enough with Postgres, you know how difficult it is to run a high availability cluster with automated failover triggering. So coordinating all the actors that provide the service to the end user is a complex series of simple tasks. where each of these tasks can go wrong. So tasks that require different privileges and that might depend on components managed by different departments. So the risk of split brain, that is a set of applications writing to a Postgres database and another set to another database, is always behind the corner. So with Cloud Native PostgreSQL, Kubernetes is the only authority and source of truth when it comes to management of cluster resources. So if assisted by a good operator, it can make the whole business continuity management more reliable, ensuring that the Postgres database is always up, while adding the complexity required for high availability to the applications. At the same time, it controls the Postgres service, ensuring that applications speak to the database through a single interface. From a business point of view, knowing that applications can rely on Kubernetes to keep the Postgres database up helps developers focus more on what they like to do, develop. At the same time, organizational and process waste is reduced through the implementation of capabilities we have highlighted before, like infrastructure abstraction, immutable applications, include application containers, CI/CD, and therefore increase the development velocity. So the same concepts can be applied beyond Postgres in general. So these are Kubernetes concepts. So finally, relying on Postgres and Kubernetes enables all of us to retain full control of the data that we process. Certainly not something to be ignored in these days where data protection plays an important role in every business. So that's the end of my presentation. I was hoping to get a quick, like 5-minute demo, unless we have. I don't know, Courtney, what do you suggest?
Yeah, if you want to do the demo, we still have a good amount of time.
Yeah, I'm just trying to, let me see. Okay. So I think you can see this. So this is the documentation of Cloud Native Postgres. So docs enterprisedb.io. I want to briefly, go through the, the main parts. So this is the installation. So everyone who wants to try Cloud Native Postgres, you can do it now. Okay. So all you have to do is point your browser to docs enterprisedb.io and follow the instructions here. So this is the installation of the operator. There's a section called Quick Start that explains how to deploy a cluster. And there's a section about samples. So here you can find some examples of the manifest if you want to. This is the full example of a manifest with all the available options. Here there's the plugin, Cloud Native Postgres plugin, how to install it with the commands. This is also a very important page that recaps all the operator capability levels that I mentioned earlier. So this is, I think, a very good page. Anyway, I'm going to start. Hopefully everything will go fine. So I have a kind cluster. So basically kind is Kubernetes in Docker. So kind get cluster, get clusters. I have a, the same. If you follow the documentation, you will have the same cluster name. So kind create cluster --name PG. So that takes probably a couple of minutes. So I've already done it. I've got this empty cluster here. I copy this command, and that's how I install the operator. Okay, so I can verify through the get deploy command if the operator is installed. So it's being installed. You can see the ready column will change shortly. Okay, the operator is now installed. Now it is time to install, to create a cluster. So what I'm going to do here is use this very simple example. So it's the default one. It's instead I decided to specify PostgreSQL 13.1, okay, because I'd like to simulate a rolling update. So all I have to do is apply the YAML file. So the desired state, Kubernetes will be informed about my desired desired state request. So this is an EDB job. So the job that creates the first instance. So this is a job pod with a job that once it's finished, it's completed. In the meantime, while this is happening, I'll go again in the documentation page. So you will find in the API reference section all the configuration options that you can use for each resource definition in the cluster with the operator. This is also a very important page that recaps all the end-to-end tests that we normally do for every commit. So every time we commit a patch to the operator, our pipelines automatically test that the operator doesn't break anything and that it works with all these versions in Kubernetes and with all these PostgreSQL versions. These are the tests that we do. So we test the installation of the operator, the creation of a cluster, setup of persistent volume, scale up, scale down, failover, switch over, backup, recovery, synchronous replication, and so on. So all the jobs have terminated. If you see at the start we had EDB. EDB means that we create an empty cluster from scratch. Join means that we create an instance starting from an existing PostgreSQL instance through PG-based backup. So that's how we create a replica. So now I've got these three pods. Okay, I've got example 1, example 2, and example 3 with these internal IP addresses. And I can execute, for example, the command describe cluster example that gives me, an overview of the whole cluster, which is the resource that the CRD that we write, and with the settings, and it tells me the events. This is a very important feature that we have, that we log all the events happening. Then it is important to showcase the service. So as you can see, we've got all the services that I mentioned before. For example, let's look at the cluster example RW service. It tells me that it points to this endpoint, which is the cluster 1 example. Okay. So now I have installed the CMP plugin. I want to show you the status command. So the status command tells me, the status of the whole cluster, even in terms of replication. There's also a JSON or YAML output for these, and also the verbose command that lists all the settings in Postgres as well. So now I want to try and update Postgres. So Postgres 15.2 has been released. All I have to do is apply the change, and this is what's happening. The first replica, the third, cluster example 3 is being updated and reinitialized. So this will take a few minutes because it needs to download the image. So I'll go back here to the documentation. Here it explains the rolling update procedure, if you want to know more. In the meantime, I might look at some questions while I keep these in the background. So, Kearney, how should I just read the questions? And
yeah, do you want to switch over? There's a few people wanted you to circle back to the EDB limited use license. They just basically wanted to go back to that slide and wanted to know like the difference. Do you think you could go over that?
So this one here.
Yes.
So essentially, you can visit our website and request. You can subscribe, and let me see. I can. So you go here from products, Cloud Native Postgres, free trial, and you are required to, you need to have an account. So you can register. After you have registered, you will be asked to fill like a form, and the license key will be sent to you. So the documentation actually explains that. So okay, there it is. So free evaluation. Okay. So it's, what you need to do is point to another image. So by default, we use PostgreSQL images. You can specify another image from the PostgreSQL repository on key.io for EDB Postgres Advanced. And for example, you can choose 13.2.5.1 for that. And then you need to add the license key there. There should also be configuration sample with license key. Yep, license key. Yeah. Okay.
Okay.
So I hope that answers the question.
We're right at the top of the hour, so all of the questions that came in that we were not able to answer, we'll go back to the team, circle back with you, and let you know the answer offline today.
Yeah.
Thank you again for joining us. Thank you for presenting. And just a reminder, you'll receive the recording and the slides later today.
Yeah. As you can see, the rolling update finished, and PostgreSQL 13.2 is now in the cluster. With sorry, I'll just finish this.
Yeah, no worries.
With cluster example 2 now being the primary, because there was an update. Last thing, if I have 30 seconds, I would like to try and destroy cluster example 2, which is the primary. Sorry about that. Sorry, delete pod. And as you can see, there's only 2 instances in the cluster. It says ready instances 2. And now there's 3, and the primary is number 1 again. So yeah, that concludes the demo, and this concludes the webinar as well. So thank you.
Thank you all. Have a great day.
Yep. Thank you. Bye-bye.